નમસ્કાર, હું આદર્શ છું. વેલકમ ટુ આદર્શ એજ્યુકેશન સોસાયટી. Standard 10th, Subject Science, Chapter 13, Magnetic Effects of Electric Current. So, dear students, today we will discuss electromagnetic induction. So, means generation of electric current by varying a magnetic field. So, you know that when a current carrying conductor is placed in a magnetic field such that the direction of the current is perpendicular to the magnetic field, this experiences force. So this we have studied in the previous video. See, suppose we are here, magnet will be there, okay, north south, and here if you are past current carrying conductor, you are moving, then what will happen? This magnetic field as well as this current carrying conductor, this field, this magnetic, both the force influences each other and generate a force. This magnetic field and this magnetic field interact each other and produces a force. Due to this force and motion will be producing. This already you learn. So it experiences force and this force causes the conductor to move. Now let us imagine that a situation in which a conductor is moving inside a magnetic field. So conductor you have to move it inside a magnetic field. Here coil will be, okay, like this, coil will be moving. Or a magnetic field is changing, otherwise this you have to move. This will be stationary, this you have to move. So then field is changing around a fixed motor, a fixed conductor. So what will happen? Whether the current is producing or not. So this was first studied by English physicist, first studied by the Michael Faraday in 1831. So electric magnetic induction was discovered by the Michael Faraday in 1831. So Faraday made an important breakthrough by discovering how a moving magnet can be used to generate the electric current. Now let us study by the following activities. So what we have to do, look here now. Take a coil of wire AB. So like this, these are the coils. And have a large number of turns will be there. And connect the ends of the coil with the galvanometer. So you know that what is a galvanometer? A galvanometer is an instrument that can detect the presence of the current in the circuit. Okay, the pointer remains zero. Okay, when there is no current, this will be at zero position only. But when the currents are flowing, it deflects either to the left or to the right of the zero mark, depending on the direction of the current. See, the next one, what we have to do, take a strong bar magnet. See, this is take a strong bar magnet and move its north pole towards to the end of the B here. Do you find any change in the galvanometer? Do you find any change in the galvanometer needle? This is the question asked. And now you will see that there is a momentary deflection in the needle of the galvanometer. Say to the right. Okay, when you are moving this side, so this will be right side, it moves. So this indicates the presence of the current in the coil AB. The deflection becomes zero, the momentum magnet stops. When it stops, the galvanometer shows zero reading. Now withdraw the north pole of the magnet away from the coil. So this you have to take what we are saying, take it back. Okay. Then now the galvanometer is deflected towards the left. So this one is deflected towards the left. So when you move right and when you are withdrawn, it will be left. Showing that the current is now set up in the opposite to the first. Place the magnet stationary. Okay, this you have to stationary means as it is, without moving, near to the coil. Keep its north pole towards the end of the B coil, and we see that galvanometer deflects towards the right. So this, if we have changed like this, then also we are noticing the same thing. Similarly, the needle moves to the left and when the coil is moved away. So like this observation, when the coil is kept stationary with respect to the magnet, the deflection of the galvanometer drops to 0. Okay, this observation. So what do you conclude from this? So this conclude that when the coil and magnets are both stationary, there is no deflection. There is no movement in the galvanometer. It is thus clear from this activity that the motion of the magnet with respect to the coil, the motion of the magnet with respect to the coil, or the coil with respect to the magnet, it is induced a potential difference. Induced means here produce the potential difference, and this this produces electric current in the circuit. Okay, this is the activity tells like this. Now we'll go for the next activity. See, by replacing the moving magnet by the current carrying coil. So here you have to replace the moving magnet, and then you have to take it here current carrying coil. So here this is a very important activity, dear students. Take two different coils, okay, like this, two different coils here of copper wire having large number of turns. Say that here 100 turns and here 50 turns respectively. Then insert them a non-conducting here a cylindrical roll. Okay, non-conducting here chart paper, this roll also, okay, chart paper roll. So then connect the coil. This is connect the coil 1. This is the coil 1, or here coil 1 I will write, and this is the coil number 2. Connect the coil 1 having a large number of turns. This is a large number of turns in series with the batteries, and plug key like this. You have to connect like this, and also connect the other coils. This second, okay, connect it by the galvanometer. Here galvanometer will be there. Now switch on the current or plug the key. Observation: the galvanometer there is a deflection in the needle. So you'll see that here deflection in the needle. So we will observe that the needle of the galvanometer instantly jumps. Instantly means suddenly jumps to the one side. So here when you switch on, suddenly moves. When you switch off, suddenly moves to the left. Okay. See now, again I will read this. We will observe that the potential difference is induced in the coil second. So whenever this one, so what happens, you see, you will observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to the zero. Immediately when you switch on the right side, and then again it comes to zero. And disconnect the coil and okay, disconnect it. And then what happens, you see, then again we will see that we will observe that the needle movement moves but to the opposite side, means like this side, then suddenly it comes to the zero. It means that now the current flows in the opposite direction, or in the coil second, in the coil second. So from this activity, from these observations, we conclude that a potential difference is induced or a potential difference is produced in the coil second whenever the electric current through the coil 1 is changing. When the electric current from the coil 1 is changing, or means here either starting or stopping, the coil 1 is starting or stopping. So coil 1 is called as primary. Here what we are saying, primary coil, and coil second is called as secondary coil. As the current in the first coil changes, the magnetic field associated with also changes. As the coil here current is changes, magnetic field associated with also changes, and thus the magnetic field lines around the second. See here, as the current is changes, as the current in the first coil changes, so what happens, you see, the magnetic field also changes. Magnetic field is also changes. As the magnetic field changes here, associated with the secondary coil, here also it changes. So, thus the magnetic field lines associated with secondary coil is also changes. Okay. and thus the magnetic field lines around the secondary coil, thus the magnetic field lines around the secondary coil has also changed. Hence, the change in the magnetic field lines associated with the secondary coil is the cause of the induced electric current or cause of the produced electric current. So, the electric current is produced. Okay. Now, you got the definition of the electromagnetic induction. The process by which changing the magnetic field in a conductor induces a current in another conductor, that is called as a electromagnetic induction. In practice, we can induce the current in the coil either by moving it. See, induce the current or producing the current either by moving it in the magnetic field or by changing the magnetic field. Either you can move by the moving the magnetic field or by changing the magnetic field around it. So the better convenient mostly situation is to move in the coil. That is the better method. Now this was, so you know that okay, current is produced. How to find the direction? This one is indicated by, say, the induced current is found to be the highest when the direction of the motion of the coil is at right angles. See, try to understand, dear students, the induced current, the produced current is found to be the highest when the direction of the motion of the coil is at right angles to the magnetic field. We know that this one, we will go for this one. In this situation, we can use the simple rule, that is Fleming's right hand rule. Fleming's right hand rule is here. This will be using. So you know that coil changes. Say, stretch the thumb, forefinger, and as well as middle finger. Say, stretch the thumb, forefinger, and as well as middle finger. So then what will you see, dear students? Now, you know that this to be so that they are perpendicular, so that they are, say like this you have to use, and here this should be perpendicular, okay, like this. And then you see that as perpendicular to each other as shown in the figure, okay, like this. See, if the forefinger indicates the direction of the magnetic field, if the, what I am doing, forefinger, here forefinger means which one? If the forefinger is changing, if the forefinger indicates the direction of the magnetic field, this is the direction of the magnetic field, and the thumb shows the direction of the motion of the conductor, okay, or force we are saying, then the middle finger will show the direction of the induced current. So this simple rule is used or called as Fleming's right hand rule. So this is the here to find the direction we are using the Fleming's right hand rule. Okay, got the idea, students? So here you see in this diagram actually, when current is changing, when the current is changing, magnetic field is here also changes. When you are supplying the current, a current changing, magnetic field also changes. When your magnetic field is changed here, then here also that magnetic field changes and induce or producing the electric current. Okay, so this is the way you can find out current is induced in the coil second 2 when current in the coil is changed. So this is called as a electromagnetic induction. So this direction we can easily find out by using the Fleming's right hand rule. Okay, got the idea, students? Okay, thank you. Bye bye.
Thank you for joining us.